Okay, this is part 3 of Unit 8A. We're looking at linear versus exponential growth. And we started looking at this parable of a bacteria in a bottle where it doubles every minute. So starting at 11 o'clock, then it doubles from 1 bacteria to 2 bacteria at 11:01, to 4 bacteria at 11:02, 11:03, there's 8 bacteria and so forth. So we've got that. And the bottle becomes full at 12 minutes. So the pattern that we're following here essentially is at 0 minutes it's 2 to the 0, 1 minute it's 2 to the 1, 2 minutes it's 2 to the 2, 3 minutes 2 to the 3. So if you keep going down, 60 minutes it's 2 to the 60, and this is when the bottle, which is 1 liter, is full. And so now let's take a look at, if this were true and this were, you were able to follow this, how big of a disaster this could actually be. So the first question is with our bottle, the disaster occurred because the bottle was completely full at 12. When was the bottle half full? So the initial thought for a lot of people is the bottle's going to be half full halfway through at 11:30. Turns out, though, that the bottle is half full at 11:59. Because if it's half full at 11:59, if you double the half, then that gives you to 1 full. So it's 1 half full here, and then at 12 o'clock you have 1 full bottle. If you were to be able to continue, 12:01 you would have 2 full bottles. 12:02 you would have 4 full bottles, because again we're doubling. So if it's half full at 11:59, then you double the half, and that creates the whole. And then you double the whole, that creates 2 fulls. Double the 2, that's 4 fulls. So it's kind of an interesting concept to look at it. Now, question 2 is interesting. Imagine that you were a mathematically sophisticated bacterium, and at 11:56 you recognize there's some impending disaster coming. So you immediately jump on your soapbox and warn the others, unless fellow bacteria slow their growth dramatically, the end is just 4 minutes away. Do you think anyone will believe you? And this is kind of an interesting thing to think about. So again, if we look at it this way, at noon that is completely full, so we have 1 whole bottle. So at 11:59, if we kind of go backwards, it's half full. 11:58, so we're, instead of doubling, we're cutting in half to go backwards. It's a 4th full. 11:57, it's an 8th full. And 11:56, the time where you raise the warning flag, it is only 1/16 full. So you think anyone's going to believe you? Well, at 11:59, if it's only 1/16 full, then that means 15/16 of the bottle is empty. So people are probably going to think you're crazy, because they're like, look at all this space that we have. But then again, you start doubling. 1 minute later, it's an 8th full. Then a minute later, it's a 4th full. A minute later, it's half full. And by 12, the disaster strikes. It's completely full. So, those are just a couple of fun questions to think about. So now let's look at number 26. Here, and here's a model of what that would look like. You can see that just drastic exponential growth right there at the end. So it's almost infinitely small in the beginning, but then it starts to pick up really quick as we get closer to the hour. So this next one, how many bacteria in the bottle at 11:15, and what fraction of the bottle is full? So at 11:15, again, the way you find this, how many bacteria in there, is you take 2, raise it to the power of the minute, so 2 to the 15th, which is 32,768 bacteria. And so then next we're going to look at, what fraction of the bottle is full at this time. So if we come back and look at this problem, then at 12 o'clock, it's well, let's start 11:59 and then I'll fill in the 12 o'clock. So this is like 1 over 2 to the first, then 1 over 2 to the second at 11:58, 1 over 2 to the third at 57, 1 over 2 to the fourth. That's 2 to the fourth power at 11:56. So notice that if you take the minute and the power, they add up to 60. So this is actually 1 over 2 to the 0, and 2 to the 0 is just 1. So at 11:15, you'd be 1 over 2, and then you're just finding the difference between 15 and basically 60. So it'd be 1 over 2 to the 45th power full, which is, I mean, almost infinitely small. It's 2.84 times 10 to the minus 14 power if you have a calculator that can do that. So you'd have 13 a decimal and then 13 zeros, but that's how full it is at that time. 1 over 2 to the 45th power. So again, within 15 minutes, it looks like this thing is not going anywhere because you just have like a speck in there. But then by 60 minutes, the whole thing is entirely full. Now, let's take this one step further. So if we look at the total surface area of the Earth, the total surface area is 5.1 times 10 to the 14th meters squared. So again, area or surface area, and a lot of people think of it in terms of like feet squared. My house is 1,600 feet squared, or square feet, or 3,000 square feet, or 1,000 square feet, or whatever the case may be. So these are square meters. So this is a meter by a meter, and so each of these is approximately 9 square feet when you look at 1 meter squared. So the surface of the Earth is 5.1 times 10 to the 14th square meters. So if we assume that the bacteria continue their doublings for a total of 2 hours, at which point they were distributed uniformly across the Earth, how deep would the layer be? Would it be knee deep, more than knee deep, or less than knee deep? And this is really interesting to think about. But again, just remember that the bacteria population, so bacteria after t minutes, can be modeled by 2 to the t power. And so one thing we need to assume, so we're going to assume that the volume of one bacteria is really, really small, 10 to the minus 21 cubic meters. So again, when we're looking at the size, we're going to be looking at volume here, and then we're going to compare that to the surface of the Earth, or the surface area of the Earth. But we've got to deal in volume to begin with. So that's the volume of one bacteria. So now, if we say, well, if that pattern falls after 2 hours, we have 2 to the 120 power bacteria, and that number is much too large to write. But that's how much bacteria we have. So then what we can do is we can take 2 to the 120th bacteria, and then we're going to times that by our conversion rate here. So our conversion rate is going to be 1 bacteria. So bacteria to cancel is 10 to the minus 21 cubic meters. So those cancel out. And when you do this, you get approximately 1.3 times 10 to the 15th cubic meters. So that's the volume of bacteria. Sorry, that says volume. So we've got this much volume of bacteria, and now imagine having that in one big jar and you dump it on a flat surface. So we're going to dump it on the surface area. Eventually, if it all stays on the surface, which it is going to due to gravity, but just imagine pouring it into a cake pan. If you take something that's got a volume and you cover that, it's going to cover the surface area, and then you'll be able to measure the depth. And that's what we're interested in, is the depth. So the way we find out, how deep this is we're going to take, the volume and divide it by the surface area. So we're going to take 1.3 times 10 to the 15th meters cubed, divide it by 5.1 times 10 to the 14th meters squared. And notice that meters squared cancels with meters cubed to leave just meters, so this is going to tell us the depth. And if you divide those out in a calculator, this is approximately, so I should put approximately 2.5 meters. So it means after 2 hours, you have approximately 2.5 meters of bacteria that covers the entire surface of the earth, which is definitely more than knee deep. A meter is approximately 3 feet, approximately a yard. They're close. And so this is much more than knee deep. This is over your head, and you would be very uncomfortable sloshing through all this bacteria. Now, a couple of key things. So that was just kind of fun to play with there, at least it was for me. But a couple of key factors about exponential growth. So in this case, we've looked at repeated doubling, which means with each doubling, the size of the most recent doubling is approximately equal to the sum of all the preceding doublings. We've kind of looked at that in our first couple of problems. But one thing I want to mention here is exponential growth cannot continue indefinitely. There definitely is not that much bacteria on the Earth. After only a relatively small number of doublings, these exponential growing quantities reach impossible proportions. If you think about the bacteria, the thing that happens there is bacteria, it has limitations. There's not enough food supply for the bacteria to continue growing. Temperature can slow it or speed it up, but then again it runs into constraints. And so this exponential growth actually doesn't continue because we are not swimming in bacteria. But it's just a fun thing to think about. So that's a look at Unit 8A with exponential growth, linear growth. And if you have any questions, please don't hesitate to let me know.